We'll start today with linear algebra. Okay, that is the today's session. Okay, see, linear algebra basically deals with matrix theory. It will discuss matrix theory in detail, like how it is used as a linear transformations, as well as rank of matrix, what is the application in system of linear equations, etc. So in general, we can classify linear algebra questions from gate perspective as three parts. One is discussing what are the matrix classifications, like we have learned in our +2 about different type of matrices like symmetric matrix, skew symmetric matrix, orthogonal matrix, etc. Properties of determinants. The second part is regarding rank of matrix, as well as solving system of linear equations using the concept learned in rank of matrix. Then the most important thing is eigenvalues and eigenvector problems. Okay, so these are the three sections which we cover one by one. Initially, we'll start with what is meant by a matrix, how we classify the rows or columns of a matrix as vectors and all. That is what we are going to discuss in today's class. Okay, so matrix is basically a row column representation of data. All of you know what is meant by row column representation of data. For example, suppose I have m rows and n columns. Then we then we write the order of a matrix is m by n. So I'll just give an example of an m by n matrix. Okay, I have A, B, C, D, etc. So there will be m rows. There will be m rows. Okay, m rows, and there will be n columns. There will be m rows and n columns. So the order of any matrix is specified by m by n. And if your m value and n value are different, that is m is not equal to n, then we call such a matrix as a rectangular matrix. Then we call such a matrix as a rectangular matrix. One example of a rectangular matrix is a, let us say, 2 by 3 matrix. I'll write a 2 by 3 matrix. We'll say a 2 by 3 equal to, that is, right, 2, 3, 4, 5, 6, 7. You know there are 2 rows and 3 columns. So this is a rectangular matrix. We know m is not equal to n. So this is a rectangular matrix. Now, if there is only one single row, for example, let us say a 1 by 3 matrix A. A 1 by 3 matrix. Let us take 2, 5, 6. This is a 1 by 3 matrix because one row and 3 columns are there, right? Generally, we call it a vector. So it is called as a row vector. Row vector. Okay. Similarly, if there is a 3 by 1 matrix, that is, there are 3 rows as well as only one column. In that case, also we call it a vector. Let us say 1, 2, 3 is a column. Normally, we call it a column vector. These are very important terms. This vector is the soul of the subject when we go forward. Okay. So when you have a single column, it's called as a column vector. When you have a single row, then it is called as a row vector. Okay. Since these are very familiar to you, I'll just move forward. One more thing is, if m is equal to n, then it is called as then it will come under a special class called as square matrices. Okay, then it will come under the class of square matrices. So if m is not equal to n, we call it rectangular matrix. In that we have some 2 special vectors, row vector, column vector. Another is if m is equal to n, then it is called as a square matrix. Okay, we'll see a very common square matrix which we have learned. It is called as the identity matrix. What is called as an identity matrix? Okay, let us consider an identity matrix of order, let us say 3. We know for a square matrix, if number of rows is 3, then number of columns will also be 3. So it will be a 3 by 3 matrix. So I mentioned it as I representing identity and 3 representing the order. Sometimes in some textbooks it will be written as I 3 by 3, and that is nothing but it is a matrix of 3 rows and 3 columns. And the peculiarity of identity matrices, it will have only the diagonal elements present. All other elements will be zeros. Okay, so only the diagonal element will be there, which will be ones. All other elements will be zeros. And this is a very special matrix in linear algebra, because this is one matrix which will not make any changes to other matrices when we operate it as a multiplication. Okay, there are some other special matrices. We'll discuss some of them now, and then proceed to matrices which demand the knowledge of vector concept. Okay, next is symmetric matrix. Symmetric matrix. So, if there is something called a symmetric matrix, there is another matrix called as skew symmetric matrix as well skew symmetric matrix. Okay, now both these terms demand knowledge of another term called as transposition of a matrix. Okay, so we'll see what is meant by transposition of a matrix, or commonly it is known as transpose of a matrix. In both these cases, we take transpose. Okay, so if A is a square matrix like 2, 3, 4, 5, the transpose of A is nothing but an interchange of rows and columns. So transposition is nothing but interchange of rows and columns. Okay, what will be the transpose? Then we indicate it by A to the power t. That will be nothing but rows will be converted into columns and columns will be converted into rows. So that will be 2, 4 and 3, 5. Okay, now what is meant by a symmetric matrix and what is meant by a skew symmetric matrix? Symmetric matrix is any square matrix which obeys the relation A transpose equal to A. This belongs to a very important class of matrices in our subject, and that is called as a symmetric matrix. And skew symmetric matrix skew symmetric matrix means if you take the transpose of the matrix and if you get the negative of the same matrix, then it is called as a skew symmetric matrix. We'll see examples for both. Okay, we'll see examples for both. In between, see, if you have any doubt, you can. We are not getting the presentation on screen. We are not getting presentation on screen. You're getting, right? Okay. Okay. You can ask, unmute and ask me any doubts during the session. There is no issue. Also, you can type it in your chat window if anything is not clear. Okay. Since these are very fundamentals which you have learned in +2, I'm going a little bit fast. Once we get into much core of the subject, we'll slow down. Okay, right. Now, so skew symmetric matrix is nothing but A transpose will give you -A, and symmetric matrix is A transpose equal to A. Right. Now we'll get we'll see some examples of skew symmetric and symmetric matrices in our next slide. Consider any matrix. See, for easier understanding, I'm taking 2 by 2 matrix now. Any matrix whose diagonal elements are, let us say 2, 3, and the opposite diagonal elements are 4, 4. Suppose this is a matrix B. Okay, what will be the transpose of this matrix B transpose? B transpose will be nothing but, if I take first column and write it as row, it will be 2, 4 here. If I take second column and write it as row, it will be 4, 3 here. Okay, now you can see both these matrices are same, right? Which means this belongs to the class of a symmetric matrix. Similarly, we'll see an example for a skew symmetric matrix. You must keep in mind, for all skew symmetric matrices, all the diagonal elements will be 0. Okay, for all skew symmetric. So if I'm considering a matrix C, I must first write all diagonal elements 0, because I'm taking an example for skew symmetric matrix. For all skew symmetric matrices, the diagonal elements will be 0. Now I'll put minus 3 here and plus 3 here. Let us see what is the transpose. C transpose will be, I'm taking the first column and writing it as row. So that will be 0, 3. I'm taking the second column minus 3, 0 and writing it as row. So that will be minus 3, 0. Now you can see if I multiply all elements of this C matrix with a minus 1, 0 will remain the same. Minus 3 becomes plus 3 and plus 3 becomes minus 3, which means my condition C transpose equal to minus C is obeyed. Naturally, it is a skew symmetric matrix. Okay, naturally, this is a skew symmetric matrix. Okay, now there are a lot of other special matrices which we learn. Like you might have heard about orthogonal matrices, like involutory matrices, then unitary matrices, etc. All these things we learn once we get an idea into column space and matrices observed as vectors. Okay, so for the time being, you just learned what is meant by symmetric matrix and skew symmetric matrix. We'll discuss one more thing regarding symmetric and skew symmetric matrix. I hope until this point everything is clear to you. Do I need to repeat any points? Do I need to repeat any points? It's clear. Okay. Thank you. I'll continue. For any matrix, a square matrix A, I can split it as a skew symmetric matrix plus a symmetric matrix. Okay. I can split it as two other square matrices. One is symmetric, other is skew symmetric. Let us consider a simple example. For example, if I take the matrix, let us say 7, 3, 2, 9. Okay, this is for A. Now it's not a symmetric matrix. So what I've told here is I can write A as a sum of symmetric and skew symmetric matrix. Okay. Now, if I take the transpose here, what will be A transpose? A transpose will be nothing but A symmetric transpose plus A skew symmetric transpose. Since I have assumed the symmetric matrix part is symmetric matrix is A transpose equal to A and skew symmetric matrix is A transpose equal to minus A, I can replace A transpose of A symmetric transpose as A symmetric and skew symmetric part as minus of A skew. Okay, this is the fundamental principle of symmetric matrix and skew symmetric matrix. That is, A transpose equal to A implies that is symmetric, and A transpose equal to minus A implies it is skew symmetric. So since I have assumed this part to be symmetric, I can write the transpose equal to that matrix itself. And I have assumed this part is equal to skew symmetric. I can write the transpose of that will be negative of that matrix. Okay. Now that is A transpose. And I have mentioned A as, so I'm marking this as equation number 1 and I'm marking this as equation number 2. So if I add equations 1 and 2, I'll have, see, these two terms, skew symmetric part terms will cancel out because ASK and minus ASK, they'll cancel out. Right side will be actually 2 times A symmetric and left side will be A plus A transpose. Okay. Now I have what is called as symmetric part of the matrix A. I can take this 2 to left side. So that is 1 by 2 into nothing but A plus A transpose. Okay. So this is the symmetric part of any square matrix. Similarly, if I subtract equation 2 from equation 1, I'll get 1 minus 2 equal to, see what happens. The symmetric part will cancel out now. ASK minus ASK will be 2 times ASK. That is equal to, left side will be A minus A transpose. Okay. So that is A minus A transpose. Now I can write A skew symmetric is equal to, I can take this 2 to the left side, sorry, right side. That will be nothing but 1 by 2 into A minus A transpose. Right. So this is how I can find out symmetric and skew symmetric part of any matrix. Okay, let us work out this particular example now. Okay, I'll try to work out this problem with this particular concept which we have learned. Okay, So here A is 2, 7, 3, 9. I need to split this as two different matrices. Okay, I need to split this as two different matrices. This part should be symmetric and this part should be skew symmetric. This is my condition. Okay, for that I have learned this theory, and I know the symmetric part will be obtained using this particular relation. Okay, the symmetric part will be obtained using this particular relation. So I need to get half times of A plus A transpose. Now, what is A transpose? A transpose is just converting rows into columns. So I'll write 7, 2, 9, 3. That will be A transpose. Correct? So what is going to be A symmetric part? That is nothing but half into 7 plus 7, 14. Okay, this is 14. 2 plus 9, 11. 9 plus 2, 11. 3 plus 3, 6. Right. So if I take half inside, that will be 7, 5.5, 5.5, and 3. Correct? And you know this is a symmetric part, the symmetric matrix, because you know the diagonal elements are different, but opposite diagonal elements are same. They are definitely, this is definitely a symmetric matrix. Okay. Now, how do you get the skew symmetric part? I get the skew symmetric part as half times A minus A transpose. This is the relation which I need to do, right? So that is half times, what I need to do is A minus A transpose. This is A and this is A transpose. 7 minus 7 is 0. Okay. 2 minus 9 is minus 7. 9 minus 2 is 7. And 3 minus 3 is 0. Now I can take the half inside. So that will be 0 minus 3.5 plus 3.5 and 0. See, we have obtained a skew symmetric matrix. Now, one more thing, you must get the matrix back if you add these two parts. Okay, you can check here. 7 plus 0 is 7. 5.5 minus 5.5 minus 3.5 is 2. 5.5 plus 3.5 is 9. 3 plus 0 is 3. So I am getting the matrix back. I have split it as two parts. One part is symmetric and the other part is skew symmetric. Okay. Hope the problem and idea is clear to you. Can I continue? Okay. Thank you. We'll move on to the next slide.
Sir.
Okay.
I have a doubt.
Yeah. Tell me.
Sir.
Yeah.
So instead of this one, while calculating asymmetric,
yeah.
So instead of applying half of A plus A transpose, this one, take the A matrix, you keep the diagonal matrix as it is, and then the other elements, take this one, the 2 plus 9, that is divided by 2. If we apply, we'll get right.
Once again, can you repeat the point?
We don't want to change the diagonal element to find out symmetric matrix.
Yeah.
Okay, then the other two, we have to take the other two elements, add the value, divided by 2, it gives the diagonal element, not diagonal, the other element.
Yeah, exactly what you have told is happening in this equation also. We are not, see, if you take A plus A transpose and times half, diagonal elements will always remain the same.
Yes,
correct?
Yes,
yeah,
sir.
because that is repeated.
Yes,
that is what you have explained is actually happening in this equation. Okay. So this is the formal way of evaluating this. See, once you have 3 by 3 and or 4 by 4 matrices, it might not be easy to write it from mind. So we need to have a formula to do it in a systematic way. That's right. Okay. Yeah. Okay. Anything else?
Nothing, sir.
Okay. Thank you. So we'll move on to our next topic. Okay. Right. Now we'll introduce the concept of vectors. Okay. So one thing you must have in mind is you have learned the coordinate systems and XY plane, right? So assume this is X axis, this is Y axis. And whenever I take one unit in X axis direction, that is corresponding to I vector or I cap is actually a unit vector in this particular direction. And in this particular, if I take a unit vector in Y direction, that is represented normally as j cap or j vector, right? So if I take 3 units in this direction, that is nothing but 3 times I vector. And if I take 4 times in this particular direction, that is nothing but 4 times j vector. Correct? Now, this is for a two-dimensional space. You can increase the dimensions of space as well. If I only had x-axis, that means it is having only a single dimension. If I have x and y-axis, that means it is having 2 dimensions. Now I can think of it's difficult to draw in a plane. I can think of 3 dimensions as well. Suppose this is the x-axis, this is the y-axis, and this is a perpendicular axis to both x and y. That means I have one plane here, right, which includes 2 dimensions. And once I have a vector which is perpendicular to that means the dimension has increased by 1, which means that is representing 3 dimensions, right? Now we'll learn it in detail. Okay, so for the time being, let us consider 2-dimensional planes, because that is more easy to visualize any vector in 2-dimensional plane than in 3-dimensional or higher dimensions. Okay, so I am considering a column vector A. Let us consider a column vector A. Okay. Let us consider a column vector A. 1 second. Okay, let's consider a column vector A to be A and B. Now, from now onwards, when we see a column vector A and B, it should give an image in our mind from this particular plane where I move A units in the X direction and B units in the Y direction. Okay, so this is nothing but AI plus BJ. I told you I is unit vector in x-axis and j is unit vector in y-axis. So A units in x-axis and B units in y-axis will take you to this particular point. So this is the vector which you should have in mind once you see the column AB. See, that is actually a geometric picture of this discrete numbers A and B. Suppose I take an example. Let us consider a column 2 minus 3. What should be the vector which come to your mind? It should be 2 units in x-axis and minus 3 units in y-axis, means y is positive y-axis, this one, negative means opposite side. So 2 units in the x-axis direction and 1, 2, 3 units in this particular direction. So this will meet at this particular point. So this will be the vector which is representing 2 minus 3. So similarly, any column can be visualized as a vector in 2D plane if it is a 2-dimensional column, right? And this extends to n-dimensional space. See, we will be always discussing and taking examples from 2D planes because that is more easier for us to visualize. Okay. So now let us see what is meant by vector addition. Let us see what is meant by vector addition. Or 2 columns are, if I am adding 2 columns, what will happen? Suppose I take one column S, let us say 2, 2, okay, and other column S 2 minus 2. Now, you know, 2 minus 2. Okay. You know how to add these 2 columns, right? We have learned matrix addition in +2. It's very simple. You have, when you want to add 2 different matrices, the only thing required is they should be having same order. Here we know the order of this particular matrix is 2 by 1, and this order of this particular matrix is also 2 by 1. So I can add element wise, right? So what is going to be the result of these 2 vectors added? It will be nothing but 2 plus 2 will give you 4, and 2 plus minus 2 will give you 0. Correct? So this is the result of this addition. Now you should have a picture of column vector addition when you write this equation. That is where you need the 2-dimensional plane and representation of columns as vectors. Let us see what is this point, this vector corresponding to. 2, 2 corresponds to 2 units in x direction and 2 units in y direction. Okay, so this will be 2 and this will be 2. So naturally that is the vector. This corresponds to 2, 2. Okay. Now what is 2 minus 2? 2 minus 2 corresponds to 2 units in x direction and 2 units in negative of y direction, which means downwards. So that will be nothing but 2 minus 2 here. Okay, 2 minus 2. Now, how do you add these two vectors? See, if you have learned vector addition in +2 physics, you might remember the parallelogram law. What we do is we take the first vector here. We have started from 0 and reached the first vector point. And then we start the second vector from this particular point. That is, I take this second vector from origin to this point, where it will land. Okay, I'm taking this vector of 2 minus 2, starting from 0. I have shifted its origin to this particular point. It will start from here and it will reach here, correct? This is going to be this vector now. This new vector is going to be the sum of these two vectors. That is what we have learned in parallelogram law of vector addition, right? So where this point will be, that point will land at the vector, column vector 4, 0. Correct? You can see 0, 0. I have reached 2, 2. That is 2 units to the right and 2 units to the. From here, what is happening is I need to go 2 units to the right and 2 units to the down. So that is 2 minus 2, right? From here, if I go 2 units to the right, I'll reach the point 4. That will be 4, 2. Then I must come down by minus 2. That is this value. So I'll reach the point 4, 0. Is it clear? See, I'm starting from 2, 2. I'm adding this particular vector, which means x-axis should be added by 2 and y-axis should be added by minus 2. If I add x-axis by an amount of 2, I'll reach the point 4, correct? And if I add y-axis by an amount of minus 2, I'll come down to the point 4, 0. So this is what is happening with column addition in matrices. Okay, so the resultant vector is nothing but 4, 0. I hope the idea of vector addition is clear to you. Is it okay? Actually, this is I can represent it as 2i plus 2j, and this vector is 2i minus 2j. And if I add this up, what I'll get is 4i plus 0j. That is what our point is, 4, 0. Is it clear? Do you have any doubt? Do you have any doubt? Okay. I hope it's clear to all of you. Right. Now I'll proceed. Let's see what happens if I scale a vector. Let's see what happens if I scale a vector. Suppose A is a vector represented by, we'll take the example of 2, 2 again. Okay. I scale a vector means I'm just multiplying each element of that vector by a particular number. Let us consider the scaling factor is 3. Then the scaled vector is nothing but 3 times A. Okay. So 3 times A means I need to multiply 3 with each element in this column. So 2 into 3 is 6. Again 2 into 3 is 6. Okay. So what is the effect of scaling a vector? The effect of scaling a vector is, you can see what is the initial vector. The initial vector is in the point 2, 2. Okay. The initial vector is 2, 2. This is the starting vector. Okay. If I scale that by 3 times, what happens is I get the new vector as 6, 6. So if this is 2, 2, I get the new vector as 6, 6, which is this particular point. Okay. 6 is this particular point. If I draw a vector from the origin, you can see that the direction of the vector remained the same. There is only one change, which is the magnitude of this vector has changed by 3 times. Okay, so that is the effect of scaling of a vector. It will not change the direction of the vector. It will only increase or decrease. Decreasing can happen. Suppose I use the value of half to scale the new vector A. What will be half times A? Half times A will be nothing but 1 by 2 into 2. That is 1. Again 1. Correct? So half times A will be 1, 1. naturally 1, 1 will land on this particular line itself. That will be this particular point. So you can see the magnitude of vector has reduced now, but the direction remains the same, correct? So magnitude will only be changed when you scale any vector. Okay, magnitude will be the only parameter which will be changed when you scale a vector. This is a very important point because scaling will never change the direction of any vectors. Is it clear? Scaling will never change the direction of any vectors. Right. Now we'll see matrices as column spaces. Now once you have the idea of vector clear to you, that is, once you feel each discrete values in a column, you map it into this particular space, you will be able to understand what a matrix means in column space. So should I break for any of your doubts? If this idea is very clear to you, I can proceed. Okay, hope nobody has got any doubts. See, you are free to unmute and ask anytime. Okay. Right. So we'll see what is meant by matrices as column spaces. Okay. Let us consider matrices as column spaces. Matrices and column space. Okay. See, I'll take the simplest matrix which we have learned. The first special matrix which I introduced to you is identity matrix. So I'll take a 2 by 2 identity matrix. That's very important. See, I 2 by 2 is nothing but it is 1 0 0 1. Okay, 1 0 0 1. Now you can say this matrix is having two columns. This is column C1. This is column C2. Okay. Now, if I visualize that matrix as two vectors, what I will represent? 1 0 is a column which is representing a vector of 1 unit in the x direction and 0 unit in the y direction, right? Which means that is representing this particular vector, right? Similarly, 0 1 is a vector which is representing 0 unit in the x direction and 1 unit in the y direction. So I can say this is the second vector. So once you see this matrix, okay, if these two vectors can be picturized, then you can understand a combination of these two columns, okay, can take you to any point in this xy plane. For example, suppose I want to represent this particular point. This particular point is nothing but, let us say, this particular point is 5 and 4 units up. Okay, so that is nothing but 5 4, or x component is 5 and y component is 4. You can say 5 4 point can be obtained using these two vectors linear combination. What is meant by linear combination? Linear combination is nothing but a weighted sum of any vectors. Linear combination of vectors means weighted sum of vectors. So I should weight this vector I mentioned as column 1, and I should weight this vector with two different values, and I must be able to get the point 5 4, right? Let us consider C1 into 5. If I take C1 into 5, or 5 times C1, you know 5 times C1 means we have learned what is meant by scaling. 5 times C1 will not change the direction of C1. It will just scale the magnitude of C1 by 5 times. Correct? So initially magnitude of C1 was 1. Correct? 1 0. So scaling it by 5 will stretch it to that point. It will not change the direction. Right? And if I take 4 times C2, what happens? There is the direction of C2 is upward, simply upward. It will not change its direction, but it will change the magnitude by 4 units. So what actually happens is, you can see what happens. 5 times 1 0, correct, plus 4 times 0 1 will actually land you in 5 into 1, 5 into 0. So that is nothing but 5 0 plus 4 into 0, 4 into 1. So that is nothing but 0 4. Now if you add up these two vectors, you will get the point 5, 4. Now, when you simply think of any possible combination of C1 and C2, you can say that you can represent any point in this XY plane as a combination of C1, C2. You want me to give another example? Let us consider the point, let us say minus 2, 2. Minus 2, 2 will be X direction minus 2, Y direction 2. So this will be the vector minus 2, 2. It's nothing but minus 2 times C1 plus 2 times C2. Correct? Because minus 2 times C1 will be minus 2, 0. And 2 times C2 will be 0, 2. So I'll get the point minus 2, 2. Now, it's very clear that these two vectors can actually give you, or a combination of different combinations of these two vectors can give you any particular point in this particular space. And then we call it, these vectors will span this space. If the linear combination of two vectors can reach to any particular point in a particular space, then the two vectors are said to span that particular space. Here we have a two-dimensional space, and a two-dimensional space is actually spanned by these two column vectors. So I can say this particular matrix will span a two-dimensional space. So that is about two vectors and linear combinations spanning the XY plane. Is it clear to you? Is it clear to you? Right. So we'll actually break for 5 minutes. In between, if you have any doubts, you can either chat it or ask me once I'm back. Okay. So we'll break for 5 minutes. Okay. See if you can think of all the points which I've discussed and ask me if you have any doubts once I'm back. So we'll be back by 5:20. Okay. Now it's 5:15. we are giving importance to column vector can sum non-vector vector to meet since it is identity matrix. Okay. Okay, I'm back. So I'll explain your doubts. Can you explain spanning 2D space again? Sure, I'll explain 2D space again. Why we are giving importance to column vector? Some can be drawn with row vector too. Okay, right. Since it is an identity matrix, those will be clear once we are getting into eigenvalues and eigenvectors. A matrix will always be getting more meaning once we take the columns as vectors. That we'll learn once we go through the subject. Please explain the spanning of vectors. Okay, right. I'll explain the spanning of vectors once again. Okay, we'll take a different example. Is that fine? We'll take a different example. Okay. Right. Suppose I take another matrix. Let us say A is now nothing but 5, 0, and let us take 2, 2. Okay. Now, let us draw these vectors now. Okay. 5, 0 is a vector in the x direction alone because I have x value as 5 and y value as 0. Okay. So this is going to be 5, 0 will be a vector here. 5, 0 vector here. Then 2, 2 will be a vector having x component of 2 and y component of 2, which means 2 in x direction and 2 in y direction. So that will be a vector pointing in this particular direction. Okay. So which point I'll get? This is 2, 2. Okay. Which point I'll get if I just add these two vectors? That will be 7, 2. Correct? If I add these two vectors, 5 and 2 would be added to give the point 2. Sorry, 7. And 2 and 0 will be added to get the point 2. Right? That I can attain in this picture by drawing or completing the parallelogram. Right? So I have drawn a vector parallel to this 5, 0 vector from here and reach this point. So this point, this particular point will be 7, 2. Right? Now, spanning a space means I need to reach to any point in this particular plane with these two vectors linear combination. Right? Suppose I want to have another point. Let us consider a point. You take an arbitrary point of 9, 3. Okay. So 9, 3 means I need to get 5, 0 is the one column and another column is 2, 2. Right? Another column is 2, 2. C1 and C2. Suppose for example, for easier understanding, I'll take the point 9, 2. I need to get 9, 2 as the result. Okay. I need to get 9, 2 as the result. And, sorry, for linear combinations of easier values, I'll take 9, 4. Right. 9, 4. I need to get 9, 4 as the result with some linear combination of C1 and C2. Is that possible? Suppose you take the value of 5 one time C1, and if I take 2 times C2, what will happen? 1 times C1 and 2 times C2 will give you 5 plus 2 times C2 is nothing but 4. 5 plus 4, I'll get 9 here. Right? 0 times C1. So 1 times 0 is 0. 0 plus 2 times 2 is 4. So that is 0 plus 4. Which point am I getting? I'm getting the point 9, 4. Right? So that is one point here. It is 9 and 4. This particular point is spanned by 2 times C1. Sorry, 1 times C1 plus 2 times C2. Similarly, if you arbitrarily take any point in this particular plane, that can be written as a combination of these two vectors. A weighted sum of these two vectors. That is the meaning of spanning this particular plane with these two vectors. it is very easy to understand once you know that different combination of these two vectors, weighted sum of these two vectors will reach you to any particular point in this plane. That is the meaning of spanning a two-dimensional space. We generally call it, we span the R square space. This 2 is indicating the dimension. R square space means real space in two dimensions. Okay. Similarly, I'll give another particular example. Suppose I have a vector, a matrix, let us say 1, 1 and 2, 2. Okay. 1, 1, 2, 2 is another matrix. What will be the column vectors representing? 1, 1 will be a vector in this particular direction, right? 1 unit on the x-axis, 1 unit on the y-axis. So that is 1, 1 vector. 2, 2 will be a vector on this particular direction. Same direction, I will have 2, 2 also. Now you can say that it cannot span the complete space, because whatever be the combination of these two columns you take, you will always lie on this particular line. Let us see, this is C1 column 1, this is column 2. Let us take an arbitrary combination of 5 times C1 and let us say 3 times C2. What will happen? 5 times C1 will be 5, 5, right? And 3 times C2 will be 6, 6, correct? 3 times C2 will be 3 into 2, 3 into 2, 6, 6. And the result is going to be 11, 11, correct? So that is again lying on this particular line, correct? So I cannot span this space now. With these two vectors, with these two particular vectors, I cannot span the complete space, but I can only span this particular line. In this particular line, I can reach anywhere. Suppose you want to reach this particular point, -1, -1. That will also be lying on this particular line. That is possible. How is that possible? Suppose I take 5 times C1 minus 3 times C2. What will happen? 5 times C1 will be 5, 5, right? And see, you must not present in between. Accidentally, you should not click the present button, because then my screen will not be visible to you. Hope it is visible now. Okay. So 5, 5 minus, okay, 5, 5 minus 3 times 2, 2 is 3 into 2, 6, 3 into 2, 6. So that is 6, 6, correct? So I'll get the result as -1, -1. Again, it is lying on the same line. So this particular matrix is spanning only one dimension. This particular matrix is spanning two dimensions. This particular matrix is spanning only one dimension, because it will give all points on this particular line, right? But this matrix will give all points on this particular space, xy plane. All points in the sense when you take different linear combinations of C1 and C2. Here also different linear combinations of C1 and C2 will land you on this particular line. So this is about spanning a one-dimensional space. This is about the matrix. First matrix is about spanning a two-dimensional space. Now I hope it is clear. Can you do 9i 3j with a matrix? The first matrix 9i 3j. That is what you need. Okay. Someone has asked a doubt. Okay. Let us consider his doubt. Okay. I'll just draw it here itself. You want to reach the point 9i 3j, correct? Someone has asked it out. He wants to reach the point 9i 3j with this particular matrix. Okay. So I will write C1 into some combination alpha plus C2 into some combination beta should reach me to the point 9, 3. Is it correct? Which means I'll consider alpha times 50 plus beta times 2, correct? Must get me the result of 9, 3. Correct? Right. So here we will get an introduction into system of linear equations also. This is why the vector concept is very important. Okay. Okay, what it means now. Alpha times 5 is 5 alpha plus 2 beta equal to 9, correct? 0 alpha plus 2 beta equal to 3. So beta should be equal to 3 by 2. And so 3 by 2 into 2 will be 3. Alpha should be 1 second. Beta should be equal to 3 by 2. And alpha should be equal to, this is 3. So if I take it to the right, it will be 6 by 5. Right? I'll explain again. I don't know what combination will reach me this point. Right? So I have arbitrarily taken that combination to be alpha and beta. Alpha times first column plus beta times second column should get me 9, 3. Correct? Alpha times first column plus beta times second column should get me 9, 3. Which means I should write it in this particular format first. Now, alpha into 5 plus 2 into beta should be 9. 5 alpha plus 2 beta equal to 9. Alpha into 0 plus 2 into beta equal to 3. See, this is a set of equation with 2 variables and 2 equations. You can easily solve it. The result will be beta equal to 3 by 2 and alpha equal to 6 by 5. Okay, Shahin has actually answered it well before I have explained. Thank you, Shahin. That is the correct answer. Okay, so you can similarly get to any point using these two vectors. That is what is meant by spanning a two-dimensional space. Hope it is clear for you, Sriram. Okay. Right. Shall I move to the next point? Okay. Right. Yes. Okay. So the spanning is fundamentally what I have explained so far. Right. Now we'll see what is meant by, let us say, determinant of a matrix. Okay. For example, suppose I take a matrix like, let us say A is equal to 3, 0 and 2, 2. A is equal to 3, 0 and 2, 2. Now you can always visualize, see, we'll be always drawing this plane now, because everything we learn in this matrix linear algebra part is related to space. Okay, so 3, 0 is a vector in this particular direction. Okay, 3, 0 is a vector in this particular direction. So this is 3, 0. Okay, now 2, 2 is a vector in this particular direction. That is 2, 2. Right? Now, if I complete this parallelogram, okay, if I complete this parallelogram, you know this point will be 2 plus 3. So this will be 5 and 2, because 2 plus 0 is 2. 2 plus 3 is 5. Okay, this will be the parallelogram. Now, you know what is the area of that particular parallelogram? The area of the particular parallelogram can be easily found using, when we divide this particular parallelogram into 2, it will have two triangles. Each triangle will have same area. Suppose I consider the area of this particular triangle alone. These are two congruent triangles, so it will have same area. So if I take the area of this particular triangle alone, that will be half times base into altitude. Correct? That is nothing but half times. What is the base length here? Base length is 3 units. 3 into what is the height here? The height I know it is upwards 2 units in y direction. Correct? Or this point is actually 2, which means the height is 2. So I can get that value as half into 3 into 2, which is equal to 3. How did you get 5, 2? Okay. Okay, that is one point. So see, I'm starting from this point and I'm shifting this vector, right? So I'm actually adding these two columns, correct? So 2, 2 is this first point, and if I add 3, 2 to that, sorry, 3, 0 to that, that will give me 3 plus 2, 5, and 2 plus 0, 2. That is how I got the point 2, 2. This is regarding your doubt and more. Okay. Is it clear? 2 plus 3. I am writing this particular vector I am taking to the upward. I mean, from starting from 2, 2. So 3 units here. So 2 plus 3, 5. Right? And this has not changed. Y direction not changed. So that the value is remaining the same. 2. Is it clear? Okay. Now, see the triangle area. What is that? Half into base into height. Base is 3, height is 2. So half into 3 into 2, that is nothing but 3. Now you have this part will also have an area of 3 because they are congruent triangles. Because they are, can we write it as 2 C2 plus C1? Yeah, correct. It's C2 plus C1 only. That's C2 plus C1 only, sir. Correct. Right? So the area of this triangle plus this triangle should get me an area total 6. Now this parallelogram is actually giving me an area of total area of 6. Now you just see what will be the determinant of this particular matrix. I hope all of you know how to take the determinant of the matrix. You just multiply diagonal elements and subtract the product of opposite diagonal elements. That is equal to 3 into 2 minus 0 into 2, which is equal to 6. Now that is giving you actually the area, which means this determinant of the matrix is actually giving you the area of this particular parallelogram. Okay, we'll see that in more detail. For example, suppose I scale one column by 2. Okay, what will happen? Suppose I scale one column by 2. That is, I have two columns C1 and C2. Okay, I have two columns C1 and C2. C1 is this particular column. C2 is this particular column. If I multiply C1 by 2, that is, I am changing one column into sit0. Other column I am remaining the same. This column is multiplied by 2. The other column is kept at same, 2 itself. Okay. Now what is going to be the result? I'll draw again. Sit0 is this particular vector. Okay. It will have a unit of sits here. 2 is the same vector, the old vector itself. Okay. Now the determinant of this matrix, what I told is, it will give you the parallelogram area, which you get by forming as using the vectors as sides. So if I complete this parallelogram, this will be the parallelogram, right? And I know if I consider this as two triangles, this triangle 1, this triangle 2, both will have same area, right? So the base is 6 now. So half into 6 into height is 2 now, correct? Half into 6 into 2, what happened? Area is 6. 6 for this particular angle, 6 for this particular angle. So total area will be 6 plus 6 equal to 12, right? Now you can see what is the determinant of this particular matrix. It becomes 6 into 2 minus 2 into 0. That is nothing but 6 into 2 minus 2 into 0. That is equal to 12. So that gives you an important point. That is, if you scale any column of a matrix by alpha, the determinant will also scale by that same value. Okay, because this 2 by 2 matrix, I had the area given to be, or determinant given to be 6. When I scale one of the columns, when I scale one of the columns by a value of 2, I got 6, 0, 2, 2 as a new matrix, and the determinant has become 6 into 2, which is 12. So that is a very important point. We'll write it in the next slide. That is, if determinant of A is equal to, let us say, delta, okay, then if any column of A is scaled by alpha, any column of A is scaled by alpha, the new determinant will be alpha times delta. This is what we have just proved. Now, what will happen if all the rows or all the columns of a matrix is scaled by the same number? Suppose A is a 3 by 3 matrix. Okay. So naturally, scaling any column will make it alpha times delta. Okay. So if I have 3 columns, alpha into alpha into alpha times delta, which is equal to alpha cube times delta. That is, if A is an n by n matrix with determinant of A given to be delta, then alpha times A. You must know alpha times A means every element of A will be scaled. For example, suppose 2, 3, 4, 1, 2, 1, 3, 4, 3. If this is A, what will be 3 times A? 3 times A means each element of A will be scaled by 3. Correct? So it will be 6, 9, 12, 3, 6, 3, 9, 12, 9. Correct? So I can consider row 1 or C1, column 1 is 3 times column 1, column of this matrix, 3 times column 2, 3 times column 3. And we have learned that if any column is scaled, the determinant will be scaled by that particular value. Now, all the columns are scaled. So there are 3 columns. So in that case, it will be 3 cube times determinant. So in general, if it is an n by n matrix, alpha will be scaling n different columns. Correct? So the new determinant will be, or determinant of alpha times A will be nothing but alpha raised to n into delta. Now this is the general relation. This is a very important relation, because if you scale a matrix by a constant, the new determinant will be the constant to the power n, where n is the order of the matrix, times the old determinant. Is it clear to you? Is there any doubt? Is it clear to? Okay, clear. It's clear. Okay, fine. So this is an important point. I hope you are taking the notes down. Okay, right. So now we will consider. Okay, what will happen if you take different values for columns? Okay, what will happen if you take different values for columns? We'll see what will happen. Okay, we have taken the matrix 3, 0, 2, 2. Correct? Now you want to scale this by 3 and you want to scale this by 2. What will be the resultant vector? 9, 0, 4, 4. Correct? Which means what is happening? 9, 0. That is 9 here, 0 here. 4, 4. This is 4, 4. Right? 4, 4. Right? Now, see, I have come. Actually, I need only this triangle's area. I need to double it. Correct? So there will be half into 9 into 9 is the base and altitude is 4. So that is nothing but 18. Correct? 18 into 2, because I need to take the second triangle. That is equal to 36. Right? Now, what is the determinant? Determinant is nothing but 36 minus 4, 0. So the initial matrix determinant was 6. 6 is scaled by 3 and then scaled by 2. So that is 2 into 3 into 6. Or if you use alpha 1, alpha 2, etc. to scale different columns, then the new determinant will be alpha 1 into alpha 2 into delta. What will happen if we take different values? Sudhagar, it's clear to you? The result will be alpha 1 into alpha 2 into the new determinant, the old determinant. Okay, thank you. We'll proceed. Okay, I'll just give an introduction into what does it mean if the determinant of any matrix is 0. If the determinant of any matrix is 0, if determinant of any matrix is 0, what does it imply? We'll consider a particular case. Let us consider the case of, let us say 2, 3, and minus, or let us say 4, 6. Okay. This is a particular matrix. We know the determinant is going to be 0 because 2 into 6 is 12. 12 minus 4 into 3. The determinant of this particular is nothing but 0. Correct? So, see, it's very easy once you have the pictorial view of this particular matrix. See, you have 2 columns. One is 2, 4. 2 units here, 4 units up. So, this is that particular vector. Okay? Now, the other is 3, 6. 3 units here, 6 units here. So, the other vector is also, this is 2, 4 vector. Okay. Now, 3, 6 vector is actually lying on the same particular direction, which means, you see, I cannot form a parallelogram with this same direction vectors. Naturally, the determinant should be equal to 0 because the area formed by the parallelogram is actually 0. So that is the meaning of determinant equal to 0. Now, that should give you another insight, because if determinant is equal to 0, which means both the columns are actually in the same direction. once they are in the same direction, they cannot span the complete space. They cannot span the two-dimensional space, which means the space spanned by this particular matrix will be one-dimensional space or a single line. Whereas the space spanned by our initial matrix, which we have taken previously, the space spanned by this matrix is actually two-dimensional space, because its determinant what is not equal to, it was not equal to 0. It was not equal to 0 means they will give two different directions, which means you can always form a parallelogram area, correct? So that is the implication of determinant of a particular matrix. Okay. So I'll just now list out some particular properties of determinant of a matrix. These are very important properties. The first property is, I have already listed, if determinant of A is equal to delta, I am considering n by n matrices here, then determinant of k times A will be nothing but k to the power n into delta. This is the first point. Okay, we have proved it, right? The second point is, this you can, determinant of the product of two matrices A into B is nothing but determinant of A into determinant of B. This you can try proving. It's very simple. See, we don't need to prove everything here, because from the gate perspective, we just need to learn this concept. Okay. If you are interested in the proof of everything, you can try it. It's very simple. Now, if you put B is equal to A here, that means determinant of, if you put B is equal to A in the above property, that implies determinant of A into A is nothing but A square, right? That is equal to determinant of A into determinant of, instead of B, I have written it as A itself. So determinant of A into A, that is equal to determinant of A, the whole square. Now, that is an important property, because that you can extend any number of times. So in general, from this particular property, I can prove that determinant of A raised to n is nothing but determinant of A whole raised to n. Okay. Now that is applicable for all positive or negative integers of n, right? So even if you have n is equal to -1, that is an interesting result, because determinant of A inverse will be determinant of A whole to the power -1, which is equal to 1 by determinant of A, correct? So this is an interesting result. Determinant of A inverse will be 1 by determinant of A, right? Also, one more property you need to learn, that is determinant of A transpose will be always equal to determinant of A. Determinant of A transpose will be always equal to determinant of A. So these are the 4 points regarding determinants which you should never forget. Okay. Have you written it down? Now, I'll give one gate problem from this particular topic, and I'll give 2 or 3 minutes to solve. Okay, after that I'll solve it. So let us consider a case of, suppose A is a particular matrix given to be 9, 2, 4, 1. Okay. Now you are asked to find the determinant of, A to the power 2021 minus 3 times A to the power 2020. You need to find the determinant of this particular matrix. What will be the answer? You can try it. I'll give 2 minutes time. If it's clear to you, you can try. If any of you get the answer, you can write it down. Okay, you are getting -2 as the answer. Okay, there is some mistake which you might have made. So we'll go into the previous slide. The previous slide is this one. These are the four properties which I have listed. You can use any of these properties, but you should not use anything other than what I have listed here. Okay, so let us see one property which you might have used. See, determinant of A plus B is not equal to determinant of A plus determinant of B. Okay, so if you have used it as equal to, you'll get the wrong answer. Determinant of A plus B is not equal to determinant of A plus determinant of B. That's wrong. Okay, some other answers are coming up. Dheeraj, Sudhakar, Atira, your answer is 2020. Okay, it's wrong. Okay, we'll see. This is a thing which you should keep in mind. If you use equal to sign here, you will end up in wrong answer. Okay, so Ishwara, you got the correct answer. It's -20. Okay, so I'll try to solve it now. Okay, let us see how it comes. Okay, so that is one thing you should keep in mind. Determinant of A plus B is not equal to determinant of A plus determinant of B. Okay, now see, I have this particular matrix A raised to 2021 minus 3 times A raised to 2020. I can always take A raised to 2020 is a common in these two part. So I can take A raised to 2020 as common, and I can write A is the balance here. A raised to 2020 into A becomes A raised to 2021. Minus, you cannot simply write 3 because 3 is a number. If you are taking a matrix with a scaled value, that is nothing but 3 times I. Okay, so that is if you write 3 into A as, okay, wait. If you have 3, 0, 0, 3, that is nothing but 3 times I. Okay. Similarly, 3 times A to the power 2020 means if I am taking A to the power 2020 outside, the what is left out is 3 times I. Now I have two matrices as product, right? Two matrices as product. So I can write if I want to write the determinant of this thing that is equivalent to determinant of the right side. So this is one matrix and this is another matrix. Now I have determinant of A into B, that is determinant of A. This is equal to, if I consider this as first matrix and if I consider this is second matrix, it's product of two matrices. So I can write determinant of A to the power 2020 into determinant of A minus 3A, correct? Into determinant of A minus 3A, because that is product of two matrices. Now determinant of A to the power 2020 is nothing but determinant of A whole to the power 2020, right? Into determinant of A minus 3A. This is what I need. Now what is determinant of A? 9 into 1 minus 4 into 2, which is 9 minus 8 equal to 1. So here I have 1 to the power 2020. So the left side, this part is always 1. Now the second part is A minus 3I. What should be A minus 3I? A is the term, 3I is nothing but 3 times identity matrix. So 3003. So if I subtract 3003 from A, the result will be 9 minus 3, 6, 2 minus 0, 2, 4 minus 0, 4, and 1 minus 3 minus 2. Okay. So what is the determinant of this particular matrix? This is what is A minus 3A. 6 into minus 2, minus 12, minus 4 into 2, minus 8. So minus 12 minus 8, it is equal to minus 20. So this part is minus 20 and this part is 1. So the product answer is minus 20. This is the correct answer. Okay, Sajeev Chandran got a correct answer. Lakshmi also got a correct. Lakshmi Anchana also got a correct answer. So hope it is clear to you. You have any doubts? Should I repeat the explanation for this one? Okay. No. Yes, it's clear. Right. So we'll stop here. We'll continue with our discussion for the inverse of matrices and for few more problems from determinant side in the next class. Okay. So if you have any doubts, you can ask it. In between, I'm stopping the recording. Okay.